Hi guys, I hope everyone is doing great. Our aim in this video, part 1, is to use the method of superposition to determine the maximum elastic deflection of a cantilevered beam. The beam is fixed at one end and supported onto springs at the other end. The beam is to also carry a uniform distributed load. The reason I actually chose this topic is because we come across this model very frequently in our day-to-day designs. A good example of spring supports could be soil, which has a particular stiffness, or what is also called a modulus of subgrade reaction. Sometimes we could have a strip footing or a stiffened raft slab on ground, and the soil could be modeled as a series of area springs or line springs underneath the footings, and this could be further modeled using a finite element software. And oftentimes we could also have a suspended slab onto piers or piles, and these piers are founded into soil. So again, soil supported under these piers could be modeled as springs. Let us take a simple example of what I'm trying to demonstrate here. In this example, we have a cantilevered concrete T-beam fixed at one end and supported onto a concrete beam at the other end. Hypothetically, this T-beam could be taken from a suspended raft or a waffle slab. The concrete pier at the end is founded into soil, and the soil has a modulus of subgrade reaction of 1,500 kilonewton per meter, which is the stiffness. This really means that the soil has the capacity to compress 1 meter under a load of 1,500 kilonewton. Theoretically, there are 6 degrees of freedom at the springs supports. However, for simplicity, we will look at the problem with a single degree of freedom to allow for a vertical translation only. Although the spring could be in tension, but for this example, we have compression only. So, we will ignore any rotational or lateral movement of the springs. I guess if we are using the stiffness method of analysis, then we could probably work out these extra parameters if needed. So here we want to work out the maximum immediate elastic deflection at the springs. So the information given in this problem is as follows. 1, we have the beam length, which is 3,600 millimeters. The soil has stiffness K 1,500 kilonewton per meter. Young's modulus of the concrete, E, is 24,000 MPa. The uncracked moment of inertia of the concrete is 1.23 times 10 to the power 9 millimeters to the power 4. EI, we call that the flexural or bending stiffness, which is simply E times the Young's modulus times the uncracked moment of inertia, is 2.95 times 10 to the power 13 Newton millimeter squared. And we also have the factored load W given to be 25 kilonewton per meter. Before we start, there are 6 important assumptions that we had to make prior calculating the deflection. Number 1, we assume that the beam is supported hard onto the pier with no gaps, which means we will ignore adhesion, pull down force, and any side friction onto the pier. 2, for the sake of simplicity, we will assume to some degree that the soil is elastic. Otherwise, it would be a complicated problem, and we'd probably need to use a nonlinear analysis approach. 3, we will ignore the self-weight of the pier and assume that the pier and the T-beam are one unit throughout the entire vertical translation. 4, we will assume that there will be no volume changes in the concrete pier due to axial compression, i.e. axial compression forces in the pier is negligible to cause the vertical deformation. Otherwise, we would probably have to consider this in the additional deflection of the overall beam deflection. So if there was some deformation in the concrete pier, then we have to consider that in the overall deflection of the beam. So we will ignore that. Number 5, we will ignore additional deflection in the beam due to long-term shrinkage drying and creep effects. 6, we will also assume that the beam is only supported at the fixed end and then onto the pier. So there is no soil underneath the beam. It is probably the worst case scenario in this case, unless of course we have soil heave under the beam, which is a different case altogether. Okay, the calculation process. The first step is to work out the determinancy. The number of unknown reactions in this case is 4. FXA, FYA, MA, and FYB. And the number of available equations of equilibrium is 3. And we all remember the equations of equilibrium is the sum of forces in the y, sum of forces in the x, and sum of moments. So the beam is indeterminate to the first degree. In this case, the number of unknowns minus the number of available equations is 1. 4 minus 3 is 1. And that, therefore, it is indeterminate to the first degree. If the number of unknowns is equal to the number of equations, then it's statically determinate. So to make this beam statically determinate, we need to move one support, and that is the spring. So we will need to move the springs and calculate the deflection at the end due to the distributed loads only. That's the first step. Okay, so we'll calculate the deflection delta T of a cantilevered beam with a UDL, and the equation for that is WL to the power 4 over 8 EI. Look, I've memorized this, but you can, derive that from the double integration method, moment area method, conjugate method. There's many methods that you can use. You can even find it in the back of any engineering textbook. So we'll working this out. Delta T, which is the total deflection due to the load, is 25 times 3600 to the power 4 divided by 8 times 2.95 times 10 to the power 13, which gives us 17.78 millimeters. So this means that the deflection under the distributed load alone without the resistance of the springs is 17.78 millimeters. Now we need to calculate the compression displacement delta R due to the reaction FYB at the springs. Okay, I call it delta R as in delta reaction. The compression in the springs is basically how much vertical displacement did the reaction FYB at the spring cause to push back that beam from point C to point D. So we know under the load alone, without the springs, the beam deflected 17.78 millimeters, which is basically from point B to point C. Then, due to the spring reaction, okay, we will theoretically get an upward movement from point C to point D. The deflection delta R of a cantilevered beam with a point load, okay, from the reaction FYB is basically PL cubed over 3 EI, where P is the force, and in this case it's the reaction, which is FYB. So we can say delta R is equal to FYB multiplied by the length cube, which is 3600 cube, times 1000, divided by 3 times EI, which is 2.95 times 10 to the power 13. And that gives us 0.526 FYB. And please note that we multiplied it by 1000 to change the units to millimeters, to be consistent with all the units as millimeters, okay? So our first relationship here between delta R and the reaction is 0.526 FYB. And we will call this equation 1. So remember this, that will be our equation 1. Ultimately, we need to calculate delta S. But to calculate delta S, which is the compression in the springs, we need to first work out the reaction FYB. And we know Hooke's law that F is equal to Kx, which is the stiffness times the deflection. So in this case, the compression in the springs which is delta S, that is equal to the reaction FYB divided by the stiffness K, where K is equal to 1,500 kilonewton divided by meter. Therefore, delta S is equal to FYB multiplied by 1,000 divided by 1,500, and that gives us 0.66 FYB. Again, we multiplied the reaction FYB by 1,000 to change the units to millimeters. Okay, this is our second relationship between the compression in the springs and the reaction, and we will call this equation number 2. But we also know from the deflected shape, as you can see above here, that the total deflection delta T is basically equal to delta R plus delta S, where delta T is the total deflection, and that from the previous slides we worked it out to be 17.78 millimeters. So we can basically say equation 1 plus equation 2 is equal to delta T. Okay, so that basically means 0.526 FYB plus 0.66 FYB is equal to 17.78 millimeters. And then working it out, the reaction FYB is equal to 17.78 divided by 1.186, which will give us approximately 15 kilonewton. And that will be the reaction through the beam and the pier onto the soil. Now we can calculate the final maximum deflection delta S, because we found out what the reaction is, which is FYB 15 kilonewton, and from equation 2 delta S is 0.66 FYB. Therefore delta S equal to 0.66 times 15, and that will give us 9.9 millimeters, which is the maximum deflection from point B to point D. And of course we need to remember that the deflection is measured from the beam's centroid, okay, the beam's neutral axis. Also from equation 1, delta R is equal to 0.526 FYB. Therefore, delta R is 0.526 multiplied by 15, and that will give us 7.88 millimeters. So we can say that the springs has basically offset or provided a relief of 7.8 millimeters, which is a theoretical upward translation from point C to point D. So and then we did a quick check as well on that with Space Gas, which is a finite element program, and we got almost exactly the same answer. As you can see here in the diagrams below, the deflection is shown to be 9.92 in Space Gas, and we got 9.9, which is virtually exactly the same results. And the shear force reaction at the springs in Space Gas, it was 14.88 kilonewton, and we got about 15 kilonewton, which we rounded it up anyway. Very similar results. So yeah, that's it, I think. I hope this video was useful. In part 2 of the series, we will proceed to calculate the reactions, maximum bending moment, and maximum shear force in the beam. And from then on, we can then calculate the T-beam section capacity. We will actually need to draw the bending moment and shear force diagram to work out the positive and negative values, like the positive and negative moment in shears in the system. From there, then we can work out the flexural and shear capacity of the T-beam and sagging and hogging. So yeah, I think it gets pretty exciting. So thank you for watching, and we will see you in the next video.